Bright Tuty. Every student matters.
Now let's move on to the exercise here. Use Euclid's division algorithm to find the HCF of these numbers. Now the question has specifically asked us to calculate the HCF using Euclid's division algorithm. So we cannot use any other method here. So let's divide 225 by 135. Obviously 135. You know the long division process, you do it yourself. 0, then 12 minus 3 is 9, right? Then I again divide 135 by 90, 190, then the remainder is 45, and then I divide 90 by 45, then the remainder is 0. Okay, when the remainder is 0, in that step I will get the HCF. So this is my HCF. Now I will write it in Euclid's division algorithm form. So 225 can be written as 135 into 1 plus 90, right? And 135 can be written as 90 into 1 plus 45, and 90 can be written as 45 into 2. Now in this step I got my HCF. So HCF is 45, right? So in this question I use the Euclid's division algorithm to find the HCF. Okay. So let's do it for a bigger number now. 38220, and we need to find the HCF with 196. Okay. Now if I multiply this by 20, it will be a bigger number than 3822, right? Right. Let's multiply 196 by 19 and let us see what number it gives us. Then 196, 4, 2, 3724. Yes, so multiplying it with 19 will be appropriate. 3724, right? When we subtract it, 8, then 9, that's it, 98, right? And when I bring this 0 down, so it will be 980. Now I need to divide this 980 by 196, right? So it will be approximately, if I multiply 196 by 5, it will give me 980. So when I multiply this by 5, it gives me 980, and the remainder is 0. So writing it into the Euclid's division algorithm form, I can write it as 196 into 195 plus 0, right? So when the remainder is 0, that means 196 completely divides 38220. Hence, this is the HCF. We discussed this in the introduction part, that if the divisor divides the dividend completely, then the divisor itself is the HCF. So HCF of 196 38220 is 196. Okay. Let's look at this one here. 867 is to be divided by 255. So the first step would be to multiply it by 3. It will give us 765. When we subtract it from 867, 2, 0, 1, right? Then we divide 255 by 102. Let me write the first step here so that it is clear to you. 255 into 3 plus 102, right? This is the first step. Now in the next step, I will divide 255 by 102 and see what it gives us. If I multiply it by 3, it will be bigger than 255, so let's multiply it by 2. then it will give us 204. Hence the remainder is 1 5. So this step gives us 102 into 2 plus 51. In the next step I will divide 102 by 51. So 102 is equal to 51 into, you can clearly see that it is equal to 51 into 2 and it will leave no remainder this step. So 51, the divisor in the last step, in which step the remainder is 0, is our HCF. So 51 is the HCF, okay, because when we divide 102, it will give us 0 as our remainder. So the required HCF is 51, okay. Let us see what the next question says. Show that every positive odd integer is of the form this, right. So 6q plus 1, 6q plus 3, 6q plus 5. When the divisor is 6, what are the possible remainders? Possible remainders are 0, 1, 2, 3, 4, 5. So every positive integer will be of the form, the number will be of the form 6q 6. I hope the question is visible. Show that every positive odd integer is of the form 6q plus 1, 6q plus 3, 6q plus 5, right, where q is some integer. So what I have done is, I have taken 6 as my divisor. So what are the possible remainders in this case? 0, 1, 2, 3, 4 or 5, right. So when the remainder is 0, the number will be of the form 6q. When the remainder is 1, number will be of the form 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 4, 6q plus 5. So these are the only possible forms of writing a positive integer in form of when the divisor is 6, right. So every positive integer can be written in these forms. There will be no positive integer left. You give me any positive integer, I will write it that integer in this form, right. So out of these we need to talk about odd integers. So obviously 6q can be divided by 2. 2 divides 6q. This means 2 divides 6q. Hence 6q is even. When you look at 6q plus 2, you can take 2 as common, 3q plus 1, right. So 2 divides 6q plus 2, hence 6q plus 2 is even, right. So this is even, this is even. Similarly, you can take 2 as common from 6q plus 4. So this is also even. So the only possible forms for odd integers are 6q plus 1, 6q plus 3 and 6q plus 5. So these are the only possible forms for positive odd integers. Why? Because every integer will either be even or odd. We have selected the even forms as 6q, 6q plus 2 and 6q plus 4. So the rest of the forms are for odd integers, okay. An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns, okay. When they have to march in the same number of columns, so there has to be a common factor in these two numbers, right. So what are the maximum number of columns in which they can march? So we are looking for a common factor in these two, right. So if I find the highest common factor in 32 and 616, let's find the highest common factor first, then we will talk about this question. So what will be the highest common factor of 616 and 32? We can do it by factorization also, or this Euclid's division algorithm also. So if I multiply it by 20, it will give me 640. So I'll have to multiply it by 19. So let's look at this multiplication. it will give me 608, right. So 8 is the remainder in this step. Now I will divide 32 by 8. 0 is the remainder in this step. So 8 is the HCF. HCF of 32 and 616 is 8, right. So it has to march in the columns of 8. Okay. What is the maximum number of columns in which they can march? This is the highest common factor of these, so they can march in 8 columns. This is the maximum, because when there are 8 columns, then it will satisfy both these numbers. Okay. So the number is 8. Now use Euclid's division lemma to show that square of any positive integer is either of the form 3m or 3m plus 1. So the numbers are talking about 3m and 3m plus 1. So let's take the divisor as 3. If the divisor is 3, what are the possible remainders? 0, 1 or 2. So what are the forms in which the numbers can be written? So every positive integer will be of the form 3q, 3q plus 1 or 3q plus 2, right. Every positive integer will be of the form 3q, 3q plus 1 or 3q plus 2. When remainder is 0, 3q, remainder 1, 3q plus 1, remainder 2, 3q plus 2. Now we have to talk about square of every positive integer. Okay. Now if I square 3q, 3q plus 1, 3q plus 2, then what will happen is, this will be 9q square, this will be 9q square plus 1 plus 6q, and this will be 9q square plus 4 plus 12q, right. Now look at this number. We need to show that the numbers are of the form 3m or 3m plus 1. These squares are of the form 3m or 3m plus 1. So if I take 3 common from this number, I will be left with 3q square inside. So this number is of the form 3m, where m is equal to 3q square, right. So every positive integer can be of these forms, and square of every positive integers can be of these forms. So these can be written in these forms. Okay. So now I am trying to manipulate these terms to bring them in the form 3m or 3m plus 1, right. So this term can be written in the form of 3m, where m is 3q square, right. Now let's look at this. If I take 3 common from these two terms, so what will it give me inside? 3q square plus 2q, right, plus 1. So now this form is of the form 3m plus 1, where m is 3q square plus 2q, right. So this number is of the form 3m plus 1. So when this number is divided by 3, it will give me remainder 1. So that is why this is of the form 3m plus 1. Now let's look at this number here. I can write this number as 9q square plus 12q plus 3 plus 1, right. So from this term, if I take 3 common, then I can write it as 3q square plus 4q plus 1 plus 1. Hence this number is also of the form 3m plus 1, where m is equal to 3q square plus 4q plus 1, right. So this number is also of the form 3m plus 1, which means when this number is divided by 3, it will give us remainder 1, right. So, square of every positive integer will be of the form 3m or 3m plus 1, clear. So, let us move to the next question here. Using Euclid division lemma, show that cube of every positive integer is of the form 9m, 9m plus 1, 9m plus 8. This is a similar question. Let us start with taking the numbers as divisor as 3, possible remainders 0, 1, 2. So, the forms of numbers will be 3q, 3q plus 1, 3q plus 2, right. Now, I need the cubes of these numbers. Now, up till this step, I have shown that every positive integer is of the form 3q, 3q plus 1 and 3q plus 2. Now, if I cube these numbers, then I will have to see whether these numbers are of the form 9m, 9m plus 1, 9m plus 8. Okay. So, let us look at cube of 3q. So, it will be 27q cubed. So, which is nothing but 9 into 3q cubed. So, it is of the form 9m, right, where m is equal to 3q cube. Okay. Let us look at this number here. Cube of this a cube 27q cube plus b cube, that is 1, plus 3a square b. So, 3q square into 1 plus 3ab square, 3q into 1 square. So, this is the cube of this number, right. So, now you see 9 can be taken common from this, this and this term. So, take 9 as common, this will give us 3q cube, this will give us 3q square and this will give us q, right, and this 1 remains outside. So, this can be written in the form of 9m plus 1, where m is equal to 3q cube plus 3q square plus q, right. Okay. So, this can again be written in the form of 9m plus 1. Now, we have to look at 3q plus 2 cubed. So, let us do it here, 3q plus 2 cubed. If you cube this number, then you can write it as 3q cubed plus 2 cubed plus 3ab a plus b. This is another form of writing a plus b cube. What I have done is a plus b cubed can be written as a cube plus b cube plus 3ab a plus b, or like in this I did a cube plus b cube plus 3a square b plus 3ab square, which is just to open this bracket. So, this can be written as this or this. So, here I have used this. Now, this can be written as 27q cubed plus this is 9 into 2 18q, 3q plus 2 and this is 8, right. Now, you clearly see that 9 can be taken common from these two terms. If you take 9 common, then what remains inside is 3q cubed plus 2q, 3q plus 2, right. You do not even have to open it, because 9 can be taken common from here, plus 8. So, this can be written as 9m plus 8, where m is equal to this expression, right. So, cube of every positive integer can be written in the form 9m, 9m plus 1 or 9m plus 8, right. So, this is how you will do these questions. Hence, our first exercise is over. Now, we will do some of the questions which appeared in your board examination and some extra questions based on this exercise. Then we will move to the next exercise.